Hi, I'm Steve Lowry from Energy Queensland, and this afternoon we are on the CQU University substation tour, and we're starting our tour at the North Street Spares holding yard. As you can see, the yard is being used to house a lot of our spare power transformers. We have a number of bits and pieces down the back, including instrumentation transformers and parts of our power transformers. Behind me, we've got a couple of transformers that we can talk a bit about. We've got a big one and a little one. On the larger transformer, which is a Wilson transformer, you can see that there are two sets of bushings. There's a large set on the left and a smaller set on the right. This transformer is a 132 kV to 66 kV transformer, and it's rated at 100 MVA. The larger bushings are for the 132 kV incomers, and the smaller bushings are for the 66 kV outgoers that are carrying the transformed voltage. The Wilson transformer, the large one, has a much higher rating than this smaller one. This smaller one is 66 to 11, and it has a much smaller power rating. You can tell that because the tank and the body of the transformer is much smaller compared to the larger transformer, which conducts a lot more power and operates at a much higher voltage. The larger transformer, actually, when it's in operation, will actually be filled with about 35,000 litres of oil. Alright, so now we're in a little bit closer to this large 100 MVA Wilson transformer, and one of the really noticeable features are the fins on the radiator. So this is an oil-filled transformer, and the purpose of these fins is to cool the oil. So the thing that really damages transformers is heat. Heat in the transformer can damage the insulation around the windings, and the purpose of the oil is to not only electrically insulate the transformer and its components, but also to keep it at a safe temperature so we don't damage it. The way this particular transformer operates is it has a forced cooling, so it's OF, and there's a pump that actually helps circulate the oil. Once it gets hot in the tank, the oil rises, goes through the pipework, and comes in at the top of the radiators. It falls. As it falls, it cools, and it gets pumped back into the transformer to create a circuit. By pumping the oil, we can get a higher rating out of the transformer because we have more cooler oil coming into the system, and we're able to keep those windings at a cooler temperature for increased power flow. The other key feature on this transformer is that big tank up there that says Wilson transformer. That is called the conservator. So the oil in the transformer, the total amount of oil, is made up of oil that sits in the main tank itself, this big box, as well as the oil in that conservator. And any of the hot oil will move into that conservator before running down through the radiator fins to be cooled and pumped back into the transformer. Another really important part of this transformer is the on-load tap changer, or OLTC. And what the OLTC does is it actually can change the winding ratio between the primary and secondary windings of the transformer in response to changes in system voltage. So if we say, for instance, that the voltage on the 132 kV side of this transformer dips to, say, 131 kV, which can happen sometimes, the tap changer can then operate to change the winding ratio in the main tank to make sure that that secondary voltage stays within an acceptable range within that 66 kV secondary voltage. So the tap changer, it's basically a motor. So we have the control cubicle here, and we have a shaft that goes up towards the top of the main tank, and what that motor does is it physically changes the position of some contacts in the tank, and each position of those contacts relates to a winding ratio. This particular tap changer has 21 different tap positions, and that, as I said before, that can be used to compensate for changes in either the primary or secondary voltage on the transformer. Alright, so the specific details relating to this transformer can be found on the nameplate. On the nameplate here we can see that there are two ratings for the transformer, an ONAN, which stands for oil natural air natural, and we have an ODAN, which is oil directional air natural, can also be referred to as OFAN, oil forced. Now the rating, the ONAN rating, is 80 MVA, and the ODAN rating is 100 MVA, and that's the difference in rating that pumping the oil makes around the transformer. We can get an extra 20 MVA out of the unit. Now this transformer actually has 3 windings. It's got a primary winding at 132 kV, secondary at 66, and a tertiary at 11. And the vector grouping for this particular transformer is a YNAO D1. So this system we see here, this is actually the neutral earthing system of the transformer. So you can see there is a steel bar that comes off the neutral insulator on top of the tank, and this conductive bar comes down the side of the transformer. We have a couple of offset insulators, and it runs through 2 toroidal CTs. These CTs are used to measure any current flow that's flowing through this bar, and if there is a current flow, it means that we are getting a neutral return current, which means that there is clearly a fault somewhere on the system and we want to trip the transformer. These CTs will then provide inputs into the transformer protection scheme, and the transformer circuit breakers will operate to protect the transformer. Another protection scheme on the transformer is our Buchholz relay, and the Buchholz relay is on that main pipe heading into the conservator, and it's in series with the pipework. And the purpose of that Buchholz relay, which is located between those 2 green taps, is to detect any oil surges in the transformer. If there is a fault, an interwinding fault on the transformer, it will create a tremendous amount of energy and heat, and this will manifest as an oil surge that will run up the pipework and through that Buchholz relay. The Buchholz relay is set up or calibrated to detect any such surges, and it will then trigger the operation of the transformer circuit breaker in the event of an oil surge to protect the transformer and prevent a catastrophic failure. There's a small sampling point at the bottom of the Buchholz relay, and in the event that we do have a surge, we can take a sample of the oil in that surge to work out what in fact caused the fault in the first place. So oil temperature and winding temperature is a really important part of protecting a transformer, and the way we monitor that is with this system here. So this is an instrument that's dedicated to monitoring the oil temperature and the winding temperature. So there is a CT in this box which will send a signal to the transformer protection scheme if the oil temperature or the winding temperature get above preset thresholds. If the transformer is getting too hot, it's either because it's been overloaded or there's some kind of internal fault in the transformer that's creating heat in the oil. If that happens, this system operates and will send a trip signal to the circuit breaker. So a power transformer is a pretty complicated piece of equipment, and there are a number of ancillary systems that exist on the transformer to keep it operating. So the transformer actually will take a 240 volt supply to operate things like the oil pump, to operate the tap changer. There's various lighting. There's power for the oil temperature indicator and winding temperature indicator. All that sits within this cabinet here. There's a number of terminal rails for the different control systems and power systems that are on board the transformer. There's also a number of manual controls here as well to initiate the pump to operate, to initiate the tap changer to operate, and there's also a protection scheme to monitor the 240 volt system inside the transformer as well. Alright, so we've moved around to the other side of the transformer now, and there's a few more features that we can point out here. At the bottom of each of these HV bushings is an inspection hatch plate, which is basically a metal plate that can be removed once the oil has been dropped, so that bushings can be connected and reconnected. One of the key features is that we have an earthing connection from the plate to the main tank to make sure that there's no potential difference between any of the parts on the transformer, and that the whole unit is kept at the same potential. Another important piece of equipment on this one is an online oil monitor. So transformer oil is a bit like blood. We can monitor different aspects of it to determine how well the transformer is performing. This unit here is called a Callisto, and it provides real-time monitoring of certain parameters in the transformer oil. This particular one monitors hydrogen, it monitors moisture, and it monitors carbon monoxide. Increases in hydrogen can mean that there is some kind of arcing or faulting energy inside the transformer that's producing gas. Moisture is really important. If you have too much moisture in your transformer oil, then the breakdown level of the oil can drop and you can have a flashover. And carbon monoxide is also an indicator for any sort of arcing or gas production within the transformer. The third feature I'll point out on this side is a silica gel breather. As I mentioned, moisture is really bad for power transformers, and what the silica gel breather does is, in a free breathing transformer, the air will pass through it and the breather will extract any moisture from the transformer oil. These breathers are made up of silica gel beads, and they will change colour when the moisture in the they've absorbed all the moisture out of the transformer that they can. And this breather has turned to an orangey reddy colour, which means that it's full of moisture and needs to be changed.